work fine? Because I don't
Yes.
see it. Okay, great. So, hi everyone, welcome to the Industrial Problem Seminar. It's a great pleasure to introduce Dr. Faye Salmon. She is a staff scientist at the Corporate Research System Laboratory of 3M. She's a pioneer in adhesive material. She got her PhD in the University of Utah from the Department of Mechanical Engineering. And she's going to talk about seek truth, create value, and engineer's perspective on 3M science applied to life.
Well, thank you, Galad. And good afternoon, everyone. Can you hear me? Okay, yeah. So I usually talk very quietly. So if you can't hear me, let me know. So first, I wanted to thank Professor Galad Lerman and also Georgia Crow, as well as your student, Daniel Miao, our proud intern this summer, and my dear colleague, Jadi Fan, for initiated this talk with me and for inviting me here. So thank you very much. So I am Faye Salmon. Today, I'm really glad to be here, to be with our next innovators, next problem solvers, and next creators here, sitting here, to share with you some of my experience in the industry. So again, my name is Faye Salmon. I have been with 3M or in industry for, well, 20 some years already. So when I first get this invitation for this talk, I thought to myself, saying, what would be really interesting to the young scientists and students today? Well, looking around this ever fast changing world, to me, something remains time, the lasting and enduring, and that is seeking truth, create value. So let that be my talk today, and I will try to my best to help you to see how working in the industry can realize that. So first, a few words of 3M. So this is our vision. 3M technology, advancing every company, enhance every home, improve every life.
I'm sorry.
Okay, is it the?
I wanted to log into the.
Oh. Oh, okay, so I can tell, yeah. Okay, vision, 3M vision here. So if you look at that, you say, wow, that's quite a tall order. So I really hope that through today's talk, I can use some examples to convince you a little bit more or see this more picture a little bit more. So what do we do then at 3M? Well, we create or develop the products to serve our customers. And so many of the products, the brand name here, you see, you're probably familiar, and you'll be using this, especially some of the face masks over the COVID. So 3M has over $30 billion revenue every year. And among that, about almost $2 billion is reinvested into R&D. So that's how much money we spend for R&D. So all these products are really built up on 4 strengths or 4 3M pillars. And that is technology, manufacturing, global capability, and 3M brand. So what you see here is the technology platforms of 3M. Jadi and I work in the corporate research lab, one of the 4 corporate research labs. So we have a corporate research materials lab, corporate research process lab, corporate research systems lab, that's where we are, and corporate research analytical lab. So those are the 4 labs, and then together with the businesses, we have all these, cover all these technology platforms. So then you say, well, the modeling, so for Jadi and I, modeling and simulation, where you can see also there, it's one of the technology platforms among all the others, like the abrasives, adhesives, nonwovens, optical films, and the medical care, wound care systems. So then you say, okay, seeking truth, that's pretty big, word. So what do you mean exactly? How are you going to do that, right? So I thought, well, maybe to help you to understand that, I will share with you some of the things I love most. So what do I love? I love beautiful things. Very, very beautiful things. And thus, this I consider to be one of the most beautiful things in the world, because this one equation pretty much describes the physics world we're in. It describes a time-changing and the space-varying physical world that is grounded by the law of conservation. That is pretty much this equation described. So being math students, you probably, you see this many times, you might have other thoughts, but as an engineer, that's my point of view. So you can changing the parameters, changing the things, and it can describe all the kind of physical phenomena. So the blue ones I put it together, those ones for engineering mechanics, where that's my background is. So these are very beautiful things. And then for engineering mechanics, this is not quite enough yet. So we will throw in the constitutive the equations that describe the relationship between stress or strain or the deformation of the elastic body, and also kinematic equations. So that's the second one at the corner. But then, as an engineer, this equation itself is the beauty of that has to be realized by many other beautiful things. So what are they? Well, as the intelligent beings, we have wondered. We wondered, we explored. We went far, we looked far above. And we also looked down under, looking at the small things like Leeuwenhoek that looked down on a dirty drop of water, 1670s, find out all these little creatures that human beings never knew before. And that is because creating a little microscope, and he was able to see all those things. So all these things we looked, we observed, but that's not enough. We also quantified. So we started from quantifying time. The sundial there, quantifying temperature, music, sound, and light, and many others. Why these things I put on here? Because all these things to me, they're intangible. Yet human beings find a way to quantify them and also to measure them, find instruments to measure them. And these are very interesting and very important. I remember when I was little, pull out the music scores of my father's from the very dusty bookshelves and looked at the pictures of Chopin and Bach. And I was really scared and fascinated by those pictures, thinking about being a little Chinese girl and seeing these Western face, and also funny notes. But the little did I know that how profound those notes are. You see, for Chinese, we have invented music and music instrument over 1,000 years, but we never really developed a way to systematically to note or write down music in terms of the scale or in terms of the relation of each note with the adjacent note. So the ability to actually to capture these intangible things and actually quantify them, write them down, that's a very significant achievement for us. To me, that is very important. I'm always marveled at this, that we human beings, I'm glad to be one of it, being able to achieve all these things. That's really, to me, that's very profound. So we observed, we quantified, we measured, and we tried to understand. So we tried to understand ourselves, DNAs. we try to understand the world, the subatomic particles, and we try to understand our the celestial world. Like what this one, I mean, I remember I was just so fascinated by this Antikythera mechanism. I don't know if you have heard that before. And that was almost 3,000 years ago. It was discovered by a Greek island, Antikythera. So it's actually an instrument to predict the moon phase and the eclipse, and also all these astronomical sequences and positions. And that's actually being considered to be the first ever computer invented by man. So these are things just fascinating, you know, almost 3,000 years ago, they developed such precise machine. I mean, if you watch some documentary movies of this, it's just amazing. So little tricks are made to be able to precisely predict, you know, the moon, the phase, you know, especially even consider the elliptical, the orbit is not completely circular, and how they compensate that is just amazing. So we try to understand. Because we can understand, we can predict, and we can build. We build better, and so that we could go further. We could go look far, and then that's not enough, right? So we come back to the math again. So all this would be great, but we still need to distill and extract them into some simple format, in the abstract format, so that we can precisely describe all these phenomena. So we have to develop the symbols to record the numbers. Thank goodness we have these Arab numbers. If it's by Chinese numbers, it would be difficult to do all these calculations. And also we understood how to represent a 3D world in 2D. And then we also developed all the kind of machines to do the calculation. So all these things is what I call beautiful. That's truly beautiful. That's really signifying the highest achievement of mankind. So why do I choose these pictures? Obviously, I love them, but also because I either visited those places or had some indirect or direct relationship. Like for example, the Curiosity, the landing on the Mars. And we actually invited, 3M invited the chief engineer, Adam Stelzner, who was overseeing this landing, the portion of the Curiosity. And that he was, when he came to 3M, that was quite a few, some years ago, he was saying, they haven't even named the spacecraft. And it was not even called the Curiosity. It's still in the development. He said, you know, by the experience, it will be named by a second grade girl of this, because usually it's little school girls gave these spacecrafts the name. So, and that's how it is named. And he told us how it would be powered, little nuclear power engine, and to take it over, you know, to control and maneuver and finally land on the Mars. It's just absolutely fascinating. Yes. Yeah, that's the Brunelleschi's. He first, right, he was in the 14 something, had this perspective view. Before, we always made everything is flat, right? With this thing, that's Brunelleschi, who also developed the design of that dome, Duomo dome. And he was the one that actually was able to say, this is where you have the point of view, right? Or the vanishing point and point of view. So how you draw those lines, so everything will appear to be 3D in a 2D image. And that's what he did, Brunelleschi, in the 14-something hundred years ago. So to me is that, so all these things, well, then what it really represent? What it really represents is that we explore, we observe, we quantify, we understand, then we can predict and we can create better. So these are the things actually are the principles of the engineers who practice in the industry. So, and for an engineer, really nothing is more beautiful than advancing our knowledge and also transform the knowledge to the product and create the elegant solution. And that's what I strive to do. I mean, I'm not saying that I'm doing that well, but that really keeps me interested and working at 3M for more than 20 years and still working. So then you say, what do you do at 3M? Well, at 3M, we develop technologies and innovations to provide material solutions. Material solutions, to me, are one of the most elegant and enduring. So think about that. Think about the semiconductors and IC, the integrated circuit to the digital age. And that was, coming from a vacuum tube. If we're still in a vacuum tube, we would not have this kind of digital time, right? So what a simple, just one material that could revolutionize our world. So material solution. And think about another thing, really simple. We all wear glasses, high index optical plastics that make the glass so thin and so easy, we can wear them and so enduring. So material solution is truly very, to me, it's very real and very elegant. I just wanted to add this, on the hallway there, it was kind of really interesting. I saw there is a poster says, create a universe out of nothing. That's on your hallway. And I'm thinking, we engineers probably cannot do that. We have to create something with some materials, create a material solution using actual tangible things. So that's one thing I said, I'm in the math department. And also it was interesting when I went to the women's restroom there. I guess you know what it is. It's this thick of a book, Dynamic Systems and Differential Equations. So that is a book in the women's bathroom. So has to be in the math department. This is so interesting. So here at 3M, we make adhesives, abrasives, materials for wound care, nonwovens. So Jadi probably familiar with all of these because we've worked together all these things. But today I will only concentrate on the abrasives and adhesives here, those two topics. So first look at the abrasives. You say abrasives? Aren't those just the sandpapers? Not quite. So if you ever had a chance to hold up or have one of the 3M abrasive discs or belt called Cubitron 2 in your hand and look closely, you will see these little triangle plates on the abrasive plate. So instead of these irregularly shaped crushed minerals or grits, we actually have every one is a little precise shaped triangle plates. And they're all placed on there. And then so these are the things we call the Cubitron 2 and also precision shaped grain, PSG. So you will hear me talk about PSG a lot. So these PSGs cut better, last longer, and cut with cooler temperature. So, and then we also have these Trizax abrasives on the left side there. So these ones are actually made also with micro replication technologies. So here I forgot to say, these little triangles are all made by the 3M's micro replication technologies. All these little aluminum oxide little particles, made and cured and fired. So these ones actually is a little structure, the little microstructures, and actually mixed with abrasive grits inside. So these are for fine polishing works. So what does it do? Well, if you ever use computer, all the IC, right? All the silicon wafers, those things all need to be polished. We know that, right? It's the so-called CMP process, the chemical, mechanical planarization or polishing process. So you have to make that like this, right? So those ones, usually you put the silicon, the wafer against the polyurethane pad and then polishing it with a slurry on the top of it. But that pad, well, this polyurethane pad at the bottom or this yellow part here, and actually will be clogged or loaded with a lot of the debris in there. So you need constantly clean that pad so that it has the polishing efficiency to continue to polish the wafer. So that conditioner, the pad, is what 3M here makes. So this is only one of the elements. So this one thing, this little red thing, is one disc. On the disc, we have 5 these elements. And then if you look at each element, the detail, and it's like this. So all different structures. So it can polishing your computer, the chips, and also your hard drive disk substrate. So hard drive is also very fantastic technology. I don't know if I have time to talk about that, but the hard drive, we have a lot of the bits, whatever, all the magnetic material coated on there. So the substrate that can have aluminum or some kind of glass materials has to be very, very flat, right? Because your head going there, read each information is only about like 3 nanometers above your actually the magnetic material. How flat the substrate has to be. So it's really, really flat. So that is also polished by 3M Trizact. And also, if you look at your iPhone or iPad, you would have a home button, the older models, or the speaker, the holes, and all those slots being cut into the Gorilla Glass of the Cornings. And those corners or those edges all need to be polished. Again, 3M Trizact. So that's a tape, looks like tape, but if you look at it under microscope, that's what this is. So all these things, 3M technology need to be there to make them possible for our consumers. So now here, let's talk about the Cubitron 2 abrasives. So this thing is very interesting. So as you can see here in this, our simulation here, we show one of 3M Cubitron to this triangle plate versus a traditional crushed mineral. So the cutting is very different and all that. So it's a piece of engineering, the very advanced engineering and feat, and combined with a lot of material solutions. So here is my story. In the early stage, in the 2008, 2009, when we're still developing these things, abrasives. So engineers actually in the abrasive system division at 3M already worked out a lot of details of how to make these little triangles, how to actually put them on the plates. They're all tips side up. So worked out all that, and then they tested. Wow, the cutting rate performed so much improvement, so good. So they came to me. We work in a corporate lab. They said, Faye, here is our new thing. Can you do a simulation to show us this thing cut better? At that time, I've never really did any simulation on the abrasives. So it was the first time. So I thought about it. So okay, I'll try to do this. I worked it. Long story short. So I was able to get the simulation working, but the results will not always agree with the experimental data. Of course, I have never even looked at the disk yet. So I went there, I said, for me to really have a great confidence of the modeling simulation, I needed to see the real thing. What is your test? How did you do the test? Where are those disks? What are those used disks? I needed to look at them. So when I looked at them, wow, it really revealed a lot of things. These things are, due to the confidential, the constraint, I cannot talk about that, but just to tell you that to really understand this, you cannot just do a so-called simulation remotely and do it and say, oh, great, you fit with any kind of curve, saying, well, this is, look how good fit I have. At some time, maybe there is a use for that. I'm not saying it's not, but in this kind of thing, if you want to truly understand how it works, why 3M the triangles cut better, how we can design it better, you really need to know how it works. So in this case here now, I really looked at the disk and said, well, this is a much bigger job than what I initially thought, even though the simulation part itself is pretty complicated, but this is more than that. What I really need to know is first to observe, quantify, measure, analyze, then I can predict. And then I can provide actual useful information to the engineers. So that's what you see, why we're doing the things, as I said earlier, the beautiful things here. These are the things that we have to practice. So here I'm just going to show you a few of the examples, what we did. So our work is the combination of experimental technique and simulation and advanced material modeling, so that we can capture really what is happening at the interface between the grids cutting the piece of metal. So on the left there, you can see that actually that is our high-speed camera actually capturing the cutting. And that little thing, the whole height there is actually only about like 300 microns. So the whole thing, when I say this triangle shape, you see there is about like, it's less than a millimeter, like less than 500. So it's about 300 micron. That's how much. And we can see clearly it's cutting. I remember when I first got the high-speed camera working, and actually first time to see individual grids cutting, the engineers in the division said, wow, is that a smoke? I said, no, it's not a smoke. Actually, it's the chips actually forming in front of that cutting tip, that actually your grid is actually making cutting instead of what they thought would be like, you know, the crushed mineral traditionally is more of like a plowing and just pushing things away. This is actually, each one act as little single point cutting tools, cut the material. So we can do the simulation, we can understand what kind of a deformation is happening at the in the material. Here, actually, this is the shear stress, the von Mises stress. So all the metals actually is removed through plastic deformation. I don't know how many of you here maybe have some engineering or materials background. So it's all, so it's not just like you chip it off. It's actually all through plastic deformation. So if it is a plastic deformation, what happens to the metal, to the chips? If it's plastic deformation, it dissipate energy. It will generate heat. And so it will heat the whole thing. So the thing, you know, when you do the grinding at high speed, the whole thing is glowing red. So it consumes the energy. Therefore, how to design this therefore to reduce that kind of energy dissipation, reduce that the plastic deformation. Plastic deformation still needs to happen, but make it as little as possible by making the tip very sharp, so then you can reduce the cutting temperature. So, and also through this thing, I can understand why the cut and also why the tips, as you can see there in the video, it actually would fracture. And all those things really governed by mechanics and by some materials. So if I can reproduce that kind of condition that tips actually sees in the grinding, I can reproduce the fracture pattern. So that's what I did, because I understand now with this. So I remember at that time, I would often bring a big piece of a triangle, plus sort of like very brittle material. I will go to the conference meeting room, I fix it there, and I use a hammer to reproduce type of forces on the tip to show how that the triangle would fracture, and compare that triangle with the simulation, with the video. The engineers immediately understood. And I know what are really the control parameters, because I can really show them how that works. I can reproduce that, repeat that. So that's what I see is that it's not just, oh, yes, you gave me the parameter material properties, I will just simulate that. You need to get your hands dirty. You need to go to the lab to see how the things work, so that you can actually solve the problem and really understand what is really governing the whole process. So as is, I hope I still have enough time. So here, what you see here is that even though it's a mundane thing, sandpaper, but it has a lot of engineering there. So for anything that has high performance, not just the 3M product, anything that has high performance, really it has to have a lot of engineering to make it work. And so another thing is with this, I hope you will have maybe different views, understanding. So next time you see a metal surface, wood surface, whatever, very highly likely those surface has been polished, has been grinded, because it has to be, you know, usually, you know, whether it's the handle of your door, or maybe, you know, whatever the fixtures in the bathroom or in the car part, and whether it's cast or a surface treated, finished, all need through some grinding. So that's what I would call create value, even though it's mundane, but we improve the life, so we create value. So next thing here, I'm talking about adhesives. So adhesives, what do you have in adhesives? Well, adhesives, one thing 3M makes is called optically clear adhesives. So that is, where is my phone? Can I borrow your phone? So if you look at your phone, you're seeing through 3M technology. Because what this here sounds like a marketing guy, but I am proud of what I do. So if you look at the display, usually, you know, it's about like 500 micron or whatever thick. It has a lot of things on there. First is your cover glass, Corning cover glass. And then after that, it has to be a layer of after that would be the touch sensor, the ITO coded touch sensor. But in order to make a good contact, you have to bond that touch sensor to your cover glass. So there is one layer of adhesive. And of course, that adhesive has to be clear, right? So you can see through. And then below that, then you might have some other films protecting, and then you have LCD. If it's OLED, the newer models, then you will have actually polarizer on the top of it to help the color, the viewing angle and the color shifting. So there's many layers on your display, so you have to bond them all together. And that's what OCA comes. Then you say, okay, that's easy, just bond it together, right? Well, there are things, we still have to work out as an engineer. And one thing is all these things has to be cut in the iPhone shape, right? So we do the die cut. And then after that, we put the liner and then ship it. So think about it, we made all the die cut. And then all the die cut has to be very precise. Think about Mustang. If you look at, think about the car company, the Apple phone. So you have to, everything is so precise. You can't make your die cut 5 microns bigger or 5 microns smaller. No way. With Apple, they will not accept that. So you have to cut it precisely and no gooey stuff, coming out. And also after die cut, you pack it, you put it, in our Shanghai plant, you pack it in a truck and ship it to Shenzhen where Foxconn is. And in the hot summer, what happens? These are the soft, gooey adhesives. It can sag, it can creep, it can do all the things. So you have to have size, the dimension stability. So by the time it went to the Shenzhen, and now actually a lot is in Vietnam, and it still has exactly same dimension. Okay, so then what did I do here? So if you open your phone here, oh, this is a new one. So the edges there is very small, right? So you have this black, the notches, whatever. What is that? It's a black ink coated on the other side of the cover glass. And that is to hide all the circuitries and parts behind. So it's ink, it's ink layer painted on the other side of this cover glass. What is that to do with OCA? Well, OCA has to bond over on that. And then on the other side would be the touch sensor. But these ink slabs, the material, the thickness before earlier time, it was thicker. Everything was thicker. So it's like 50 microns. The OCA itself is only 80 microns or 100 microns. So you have a step of 50 micron, and you have a soft material only twice or maybe less than twice to push onto that, still cover this part, but fill this step here. Do you see what I mean there? So if you don't do that well, it will cause a so-called edge, the white edge. So the edges will appear to be brighter. So on the older phone, you probably never noticed that. We work the day and night, need to fix that problem. Because if it doesn't fit very well, it acts as a lens. So that it actually will distort the light, so appear to be brighter. So we call the white edge. Or sometimes if it's not laminated well, it will pull the LCD, if it's not the OLED. LCD, the panel, right? The LCD had these spiral crystals to structures to allow the light to go through, right? And then if you pull it, you will change that structure and the light would not go through. And you have the light, the non-uniformity. So a lot of those problems need to be solved, and all very detailed things. And you have to do that, solve those problems. You have to make your products perform day in, day out, all the time. So next time, I hope that you hold the iPhone, you think about how many engineers worked there in the lab. I mean, when Apple calls us, we go fix the thing immediately. It doesn't matter where you are, you go fix those problems. So those are the OCA, and then they were also so-called 3M VHB structural glazing tapes, and that is the actually tapes used to bond those window panels on high-side buildings. I will talk about that later. So here now, I'm not actually talking about the ink step and all those things. I'm talking about the foldable display. So you probably heard Samsung's Z Fold, Z whatever flap or whatever those things flip. So So basically, these engineers say, oh gosh, we have OLED. It's flexible. It's coated on the plastic substrate. So I can fold it. How about I make a foldable foam? So anyway, we will leave that kind of ideas for some another day to talk about it because I have my own thought. So they said, well, let's make it foldable. Okay, great. Now you make the display foldable. And then already the displays is all bound together. So now if you make it foldable, you have all these layers, cover glass now become cover plastic and all these things. So which layer do you think you have most room to maneuver to make it flexible? Among all the layers, you only the ones that you have most room to maneuver is the softest layer among all those layers there in the display. Which one is the softest layer? OCA, the 3M optically clear adhesives. And that's one of the things totally changed the OCA's role. Before it's a bonding agent. Now it becomes flexibility enabler. Without OCA, you can't fold it. You can fold it, but then you will damage it. So then that's the thing. So, okay, well, then the customer says, now we want a foldable. You got to make an OCA that actually can allow us to fold. Okay, well, that's good. The problem is we cannot get any sample from the customers. We had even now, we had very little access to the actual OLED panel. Not in the phone, we can disassemble a phone, but we can do a test on that. We don't have even OLED. They won't even tell us exactly what is in the construction. So in order to understand how the OCA needs to perform in a foldable form, we have no specimen to do test. The customer won't tell us too much about it. Yet they said your OCA has to work. So what do? Then we said, okay, well, let's do simulation modeling first. Let's see if we can understand something. And that's what we did, is we will start with the simulation and trying to answer some critical questions. So what you see here, I won't go to the detail, is that actually we were simulating a typical layout at that time. The particular, this table here actually is all the layers. And then at that time, they considered both outfold and infold. You can fold this way, or you can fold this way. So at that time, we simulated outfolding, and we simulated the dynamic folding process from folding for 3 seconds, you fold it, and then leave there for 24 hours, and then unfold and see what happens. So I won't go to the detail. But we did all these simulations, and then we identified these critical failure modes. So whether it's about the too much of a tensile stress that potentially could fracture the OLED. It's not OLED itself, but OLED has to be sealed, right? The OLED cannot be exposed to oxygen, air, or moisture. So it always has this encapsulated layer on it, and those ones are all amorphous ceramics. So those things are very tight, so it's completely sealed them. But those things are very brittle. So if you do a tensile stress, guess what? They'll crack. And then they also could have shear at the edge, and also another thing is buckling. So you have the folding, and then if you do the folding, I don't know if you can see, right? So you have the edge where you have a lot of shear, and then also buckling. And so these are the things we identified, although we don't have any specimen to do the test. We did some tests, just put 2 pieces of plastic together, bonded with OCA, did some tests, but that's all we could. And then we had the Samsung principal engineer, and with her design team came visit us, and we showed them all the works, chemistry and everything, how the OCA would work. They kept their lips tight. They never said anything. They just said, Lord. And then when I showed them these pictures and showed them saying, one failure mode we identified is buckling. And the buckling, you have 2 types of buckling, local buckling, global buckling, and where, how the buckling. And this is the toughest problem to overcome, and it needs to have a holistic approach. And then the principal engineer, she said, that's exactly what we saw in our lab. Okay. And she said, that's where the location, we saw it too. So finally they started to talk. I said, how did you do that? Well, because we tried to understand the problem, And we have the ability to really simulate our adhesives. And so all the technical contents here, what I described here about OCA, really the biggest content in terms of simulation is our ability to simulate the soft adhesive like PSA, pressure sensitive adhesive, simulated as a hyperelastic, viscoelastic, or hyperplastic type of material. And those are kind of technology we're still in the leading position at 3M, and those ones are developed, through that time. So I don't know how's my time doing here. Oh, okay, so this is quick. I'm just saying this is also VHB tape. So maybe just give you an example is you see these buildings, those glass panels. So they actually just bonded, the glass panel bonded on the metal frame, just like that by 3M's VHB tape. And then maybe at the bottom, they have a ledge to hold the weight. But other than that, the whole thing is just glued on, okay? So that's what here, and then that was me. As I said, I always like to go to the place to see that. That's another interesting place. You should go there. It's very how you see that new money to the old business, right? So the guy who founded, what was that name? I always forgot. One of the high-tech company. He made tons of money, and then he invested to this bourbon, which is also a very interesting business model. If I have a chance, I can talk to you. So that's why it's high-tech. So everything looks so fancy new, and that facade is used by bonded by 3M VHB tape. That's why I went there. Not like I like bourbon. I don't even drink anything, but I went there to see our products. So VHB tape, as just showing here, how it's done, right? So this is San Diego. So next time you go to San Diego airport, look it up there and think that's 3M VHB tape bonded it there, so you can see. So first, these things are assembled. The glass panel assembled in the factory like that. And then they shipped it to the construction site and hoist up and then being installed. And so that's what the VHB tape there is. So why is that interesting? Well, the thing is, it's on the building. It has to be there, last for 25 years. What kind of a load do you think the VHB tape, when you tape the piece of glass like that on the window frame and you're sitting inside, what kind of a load would that panel experience during the service? Think about Chicago, think about Ian, the hurricane. So when you have a wind, gust wind, blow to the building, say if I'm in the building, blow to me here. So you will have a wind load on these window panels, right? So where will that wind load be the most critical to the window panel in terms for PhD bond strength? If you have a wind go this way. So when the wind goes this way, the speed here would be very high, right? On the side of the one, and also maybe turbulence in the behind. So if you have a high speed of air, velocity, high speed, what happens? Pressure drops, right? So you have a pressure difference. Inside of the pressure is higher. Inside of your building, pressure is higher than outside. Goes one, happens is to push the window panel outside outward and put a tensile stress on our VHB tape. That's not good. Compression, that's no problem. Tension, that could fail. So we need to consider the wind load. And also we have to consider the glass panels is all heat treated, right? So annealed and all. So after that, often the glass panel is warped. It's not that flat. So if it is warped, but the construction, the metal frame is completely, straight flat. So you have a warped glass on a straight. So the VHB has to hold that, the hold on the spring back stress all this time. So that we need to consider. And during the installation, how much pressure you need to apply on that warped glass so that it will have sufficient wet out stress. That we have to consider. So all these modeling work has to be done. And then, we will do all this. I won't go to the detail, but what I'm showing here is that there's a lot of science and a lot of research and a lot of careful engineering to make sure this kind of tape would work under all these conditions. So actually the wind load there that you see at the top, that is from Chicago. So we went there to Chicago's the weather, collected last, I don't know, 70 years or something, wind data, so that we can know, for windy city or whatever. And then another one is in Florida, now the city I forgot, Florida somewhere. And so we collected all the wind load and we developed the failure criteria, characterize our VHP tapes so that we can simulate our VHP's performance in the loading condition. So here is what I'm saying, what the moral story here is really you need to understand the application conditions. You need to understand what your VHP tape need to sustain, and then to develop the right material models, write the loading models, and have the very reliable design criteria or design guidelines for our customers. So that's for the wind load. And here is recently an interesting thing that we did with Discovery Channel. So this, I hope you probably have a Discovery Channel. So just the last Halloween weekend, the Saturday and Sunday, they aired this episode. It's called Tomorrow's World Today. And so what is this I don't know if you're familiar with that show on Discovery Channel. So it actually shows 3M's VHP tape and how it's here. It's already, I put it here. So it shows, how the VHP developed and the test, the type of a test. So what we did here is that you see the simulation there. So I did that simulation in May, I think. It was also a very interesting story. That's another time's story. So we did the simulation. So they actually, the crew, oh, do I have internet here? I guess maybe I don't have internet. Oh, that's one. So anyway, if you go now, they are released because they aired. So it's on the YouTube. If you search for Discovery Channel's Tomorrow's World Today and 3M VHP tape, season 5, episode 4, what's riveting about the tape, and you can see this show. And then that one, the simulation is what I did to actually simulating what it's in a hurricane. You have this wood flying around, hit the window. So what we actually simulated here is a Stanley's storm door, a panel of the storm door. And then you will see in the earlier of the show, they actually went to the site to see they shoot a 2x4 wood, a 12 feet long wood, right to the corner. They call it corner of the panel there. And then just, it cannot shatter, it cannot debond, because that would cause damage and injury. So the one thing is you need to test, make sure that under this ASTM standard with this speed, this much of weight, mass of the 2x4, you cannot debond. And so and the shatter and everything, because these things are laminated a glass panel, so it does not shatter. It will fracture but not shatter. So that's one thing we did. So hopefully, what I'm showing here is, things we do here might look. This is interesting. Okay. Huh. I can't go back to this mode. Oh, okay, here. So. This is another story. It's really interesting. I hope I have time here. So one year I was at a conference, and then one guy came and said, "Oh, I see you are from 3M." I said, "Yes, I'm from 3M." So, "Oh, I want to tell you a story. I'm from CERN." Okay, so this Large Hadron Collider, right, in the France and Swiss border, right? The big collider, the lab. So he said, well, when they were building this lab there, they have this maintenance and construction trucks has to navigate through this narrow tunnel. What you see here, right? This narrow tunnel. And so it's all rock and everything. He said, oh gosh, it was so this tunnel here. And so it looks kind of wide, but actually it's very narrow. So they have this truck, and they have to be so careful so that they don't bump into the equipment on the left and then the rock wall on the right. And for a long time they couldn't solve the problem. That's the early time, right? So and then so one day finally one guy said, you know what, you should try 3M's traffic tape. So they tried to use computer vision. And so before nothing worked, but then they got a hand so that the whatever marketing gave them a row of 3M traffic tapes. So if you drive on the highway or on the road, you saw those traffic markers tapes. Those, if it's a tape, it's by 3M. So those white, the divide or yellow ones, those tapes, and actually not long ago, I did a simulation of all the stop bars, the white bars that right in the, the traffic light that we call the stop bar, to analyze how that fracture. But anyway, so I won't talk about that. So what they said is, so they said you should try that. So they put this one, they actually was too wide. They have to cut it in half, the length, and put it along all this path here. So then they use computer vision to aim at this thing, So now your Tesla and everything does that automatically, but that time they didn't have that. So by putting on that tape, and then their computer vision things worked because that tape is highly reflective. So now they can guide the truck automatically through the tunnel without bumping anywhere because it's already, navigated, already mapped out. So there's no way the truck will, the width would exceed the space there. So mundane, yes. Is it useful? Yes. So that's what I'm saying. The engineers is really understand the truth. Always find something you can do to help to create value, to make other people's life better. So hopefully here through my talk, you can see how we actually practice these beautiful things, explore, observe, and quantify, and build. So I would encourage you, the next inventor and creator, never stop wonder. Go out, you look at anything. To me, is anything I look at, I find it fascinating, interesting, and explore, try to understand, and also appreciate. So, anything, whatever is made, has to have a lot of engineering. If it doesn't, you will notice it. If the thing works so smoothly, it must be engineers did a great job, because it doesn't cause any pain and trouble. So appreciate that. Hold the handle. Think about someone actually developed fancy, abrasives to polish that. Use your next iPhone. Think about the chips. How many process needed to? Oh, I haven't talked about now the chips getting so smaller. How they actually doing the lithography things that. Megawatt power machine. How they do that, that's another story. It was so interesting. So appreciate it, and then you understand that all these things, the beautiful world is created by so many people working together, apply the knowledge and the talents, and to make the life better. So that is very beautiful, and that's very fulfilling, I think. So I will end my talk here, but then also, if you're interested in 3M, anything, or intern or career opportunities, send your resume to Jadi and to the website over there. So we can help and see what kind of talents you could help 3M to be better. And also, I want to acknowledge the people I have worked with. Only just on these few projects, I worked with so many people at the 3M. That's one good, interesting thing at 3M. So many experts, so many talents, so many fancy equipment. I always say, I just play my video games or play my games at work, because there's so many, whatever test I want to do, I pretty much can find a way to do that. So these are the people, always helped. So appreciate the people, appreciate each other, and appreciate this world. So thank you.
Yeah, thank you, Faye, for a really great talk. It was very useful. We do basic modeling projects in our courses, but it's very useful to see the advanced modeling that you showed here. It's a very impressive video. Yeah, so people, if you have questions, just raise your hands. And also people at home, if you have questions, please type them in the questions and answer box.
Yes.
How many mathematicians work in your modeling teams?
Mathematician, our modeling group actually all have some engineering background. So modeling is really a tool for us. But then the mathematicians is in our, we certainly have a lot of data scientists. So we have actually it's also in our so-called corporate lab, the systems lab. So we have a data scientist, a mathematician. We also have a lot of work in, we just really understand the health insurance and all those offices, we also have a lot of mathematicians doing all these statistic analysis. So that's, yeah. And certainly computer vision, you see those, we do a lot of computer vision type of work and risk construction and all of the 3D data. We have that, but I wouldn't say that many, but certainly we have, not as many as, say, chemical engineering or mechanical. Yeah. I worked there. I always had fun. Hopefully you can see that I had a lot of fun there. Every time I talk about my work, I can't stop. So are you also mathematics major?
No, we are from civil.
You from what?
Civil engineering.
Oh, civil engineering. Yeah, you saw that at Toronto, right? That's where I was there, actually looking at the shear wall. They're doing all the entire shear wall using MPS machine. And so it's so huge. The entire building is a load bearing building, so they can load all the wall to do all the different loading. It was really interesting. That's why I told you, right, at those places, basically I visited, saw it, was really fascinated, and that was one of that. Oh, civil engineer. Yeah, that's interesting. Yeah, mathematics. Yeah, so I mean, that's I don't know if we could say that, language of science, right? So that's how you really represent your world, so that you can actually do something about it, to operate and understand the relations. So at least that's my engineer point of view.
Timeline of getting back to you had this video presentation, sort of basis on curiosity, and it seemed like a very complicated project. So how long?
Yeah, that's a very good question. So if you say that the formally started, it would be 2008, and the product launched, I think it's 2011. So it's only 3 years. But that's not, because micro replication, this is a lot of micro replication technology that exists for a long time. So we basically say, use one technology and then find adjacent applications. So micro replication started from making this phenol length, right, for the projections, the thing. That's how it started. So you have to make phenol length, the length, really compress it to become basically flat instead of a big bulk, right? So that's how each length, the curvature is molded in there to make it flat. So you crush it, right? That's what the phenol length. Yeah. So that is from there, and then so those things is already there, and so all those developments was already there, and the engineers find a clever way to apply it for abrasives. Yeah, but it typically depends on, could be 10 years. And if you have a lot of things already, especially production lines is there already, then does not require that much of an investment. You probably can launch a product in 2 to 3 years. Otherwise, it will be longer, because just to make the production line, you have to invest tens of millions, if not hundreds of $millions, to just make the production line actually, so you can crunch out these sandpapers day in, day out. Yeah. Yes, that's why corporate lab exists. So corporate like take the front end development, and when the technology is more mature, and then we transfer that technology to the division, and division can quickly pick it up and then commercialize. Yeah, so that's what, you have to really, in the corporate research lab, we have to look 5-10 years ahead, saying these are, we would have a horizon 1, 2, 3. So look at a horizon 1 would be more near-term project, horizon 3 further. So we have to look at that and look at the business impact, and to prioritize our capital investment on what project to work on. So definitely, the corporate lab is looking more further down the road, developing the technology. Yeah. Yes, it's not easy to run a big business. So one thing is I often find it really disappointing if I could say this. Sometimes I saw young people protesting this, saying that they have the profit or windfall profit this, and say, yeah, maybe there are some bad apples, whatever. But majority of the people in corporate, they do work very hard trying to make the world better. They are not trying to do anything bad or whatever. They're not trying to pollute the world or kill people. No, we work trying to make our customer happy and make our life better. So and then we have to take the risk to make investment, saying, is this something customer want? Even the OCA, right? So OCA is optically clear, but actually a lot of these pressure sensitive adhesives is clear, but it doesn't have the right index, the optical index. So we said, oh, I was not involved. That's our the polymer scientist. They said, they need that, but our adhesive is clear. Can we do that? But then you have to say, okay, you have to have all the index match, right? You learn optics, or at least match as much as possible. And so then there's some things that, okay, we can modify this to make the index match so well, then it works so clear on the glass, right? Usually what 1.5, 1.4 something in the optical index. Yeah. So yeah.
What skills do you usually expect from someone that seek a career in 3M, like an entry level, someone that is just graduated from PhD?
Yeah, we have a lot of these PhD students. We hire them every year. So depends, right? 3M is really big, and we have 20-something business divisions and different 40-something, 46 technology platforms. So we need a lot of different the discipline expertise at the 3M. But foremost, I think the people who are really, I would say, have a solid training in your field, in the field of training, and also have a solid of a grasp of the real world. You are here really to solve a real problem, to really make something so that some people can use, and then some people would be willing to pay for the product to buy to benefit their life. So you have to have a real world sense of solving the problem, and also to be actually solve the problem, not just the answers. Oh, sorry if I said write an equation, great equation. What does that mean? Like abrasive. Someone did find the equation to fit all the experimental data with how many, like a dozen of parameters in it. Great. That could be useful at some time. But what does that tell? What does that tell the division to say how you're going to improve your products with a fitted equation there, with all those parameters? What does parameter even mean? But fit it all perfectly. So to answer your questions is have a good, whatever the training in your field, it doesn't matter, math, physics, and mechanical engineering. Have a sense of real world, how things work, how the company can be run to be not just say profitable. The company has to be profitable, so that we can have $2 billion for R&D, right? So that we can give the salary to support all this, the people at the 3M, and also being able to really willing to help somebody, and that's your colleague, that's your customers, that's the division thing. You go in there, and one thing, of course, then you talk about more detailed things, communication, right, and willing to try to take some risk, and then being able to to distill a complex problem to a simple thing. Say this is how we should do it, and we should solve it. So all those things, pretty much what you learn at school, especially through your PhD training in the lab, carried out to the division, to the business. At the 3M, there's advantage is that, especially now, we really pay attention to mentoring, help, and training of young employees compared to when I went there. Now, I talked to these guys all the time. Say, you guys have training, you have mentorship, you have this. I mentor quite a few people there, so you will help these young people quickly up to speed to be able to function in the multifunctional corporation like 3M. So you will have a lot of people to help you. And why these people? I mean, last year we had how many interns? We gave three offers, right? Every single one of them accepted our offer because they said they like to work with the group, right? Dan, know that. Yeah, because we help each other. Yeah.
Yeah,
So
thank you very
I know
much.
My time is over.
And we will have a follow-up section in 405. Okay, the room nearby. So, yeah.
Thank you. Okay, good.